5-digit natural number is called a fancy number provided that in decimal notation no two of its digits are the same and the leftmost digit is equal to the sum of the remaining digits. How many fancy numbers are there? Alright, well this is just an arbitrary definition of fancy number. So we've just defined it as a number where none of the digits are the same and the leftmost digit equals the sum of the remaining 4 digits. Okay, so 5-digit number. So let's see. Let's see what we can do here. We have 5 digits, and the last 4 digits have to be different. Well, actually, all 5 of the digits have to be different. And then the leftmost digit is defined by the sum of the remaining digits, right? So for example, if we have 1, 2, 3, 0, that'll be a fancy number if we add a 6 to it in the 10,000th place, okay? So there's a fancy number, all right? Now, given this fancy number, actually, so 6 is actually the smallest leftmost digit that we can have, because these all have to be different numbers, and 0, 1, 2, and 3 are the lowest numbers we could choose, okay? So, given this fancy number, we can actually create some more fancy numbers just by rearranging these last 4 digits. Okay, and they're all different digits, so how many ways do we have to arrange those digits? We'll have 4 choices for the thousandths place. We'll have 3 choices for the hundreds place, and then we'll have 2 choices for the tens place, and then 1 for the units place. Okay, so that's 4 factorial ways to rearrange the last 4 digits of this number and still get a fancy number. Okay. So now we have 4 factorial. What is 4 factorial anyway? It's 4 times 3 times 2 times 1. So that's 12 times 2, which is 24. So we can just write that as 24. So there's 24 of these numbers. Okay, well, and that's really the only way you can get 6 in the leading digit, the leftmost digit, is with 1, 2, 3, and 0. Alright, so let's look at 7. If we had a leading digit of 7, how many ways could we make 7 with 4 different digits? Well, we could do 1, 2, 4, and 0, right? And that's really the only 4 digits that work, because if I made this a 3, then I'd have to have another 3, or I'd have to have a 1 and a 2, and without repeating any digits, these are the only unique digits that will add up to 7, okay? So again, we can rearrange these last 4 digits any way we want, okay, and we'll have 4 factorial ways to arrange them, which is, again, 24. So there's 24 of these as well. Alright, let's look at 8. 8, we could do 1, 2, 5, and 0. Just add 1 more to the 4. Or we could do 1, 3, 4, and 0, right? Any other ones? Without repeating any digits, I think that's all we can do with 8. Okay. So, and each of these fancy numbers can be rearranged 24 ways to get more fancy numbers. So we have 24 of these and 24 of these. Okay. So these are just using these digits. We can rearrange the last 4 digits and get more fancy numbers. All right. Let's look at 9. Well, let's see. 9, we could do 1, 2, 6, 0. Or, let's see, we could do 1, 3, 5, and 0. Or, let's see, we could do 2, 3, 4, and 0, right? So, I'm just starting with the 8 and adding 1 to each of the different digits to get these 3 types of fancy numbers. And then, again, we can rearrange these 3 types of fancy numbers to get 24 unique fancy numbers for each of these types, okay? 24. Alright. And that's it, because if we can't, we ended up getting a 6-digit number if we go beyond 9, so, and 6 was our lowest. So we have, it looks like, 7 types of fancy numbers, and for each of those types of fancy numbers, we have 24 ways to arrange the last 4 digits. So that will give us 24 times 7 fancy numbers. So what is that? 28, so that's 168. Alright. So we can form 168 fancy numbers.